Okay, so we were doing chapter 9, which is Maxwell's equation or the Faraday's law, and where we looked at the different types of EMF, which is the motion transformer EMF, motional EMF, and both transformer EMF. And we also looked at the simple, rather than using this complicated expression, we saw a simple expression of Faraday's law, and the simple expression of Faraday's law states that where is it? So the simple expression of Faraday's law states that this one, EMF is equal to minus d psi over dt, or if it is n turns, then it is minus n d psi over dt. And this expression automatically incorporates transformer and motional both. That means you don't need to worry, the type of EMF that your problem or your, so your design is going to generate. Automatically take into consideration both, whether it is transformer, whether it is motional, or whether it is both, right? So based on that, we did some examples. Okay, we did some examples, and we also proved that yes, in fact, this expression is much handy and it incorporates any type of EMF which is generated. We did it in this example and the previous example using the long expression, and we saw that. Okay, and then we also looked at this example of motional EMF. This part I'm leaving it to you. You can do it at your home. So now, today we are going to focus on the displacement current, and we are going to talk about the displacement current. This is another example of our EMF part, but here I will not go and solve it, but I will just give you the idea. So what it is saying that we need to calculate the current induced in the rectangular loop of 200 turns, and the total resistance of the rectangular loop is given to you, which is 300 ohms. So this is my rectangular loop, and somehow this rectangular loop has a resistance of 30 ohms, and I need to find the current induced in this rectangular loop. And this is my problem statement. So you have an infinite line here, and this infinite line is carrying a current 5 sine 100t. So the current is an alternating current, and this is the loop dimensions, everything. So how are you going to proceed? Yes, how are you going to proceed? Mr. Ibrahim Al-Shamasi, can you tell me how are we going to proceed here?
Yes, doctor.
Yes. How are we going to proceed to find current in this loop? So to find the current in this loop, what we need to find first? Yes. What will be the idea here?
Find the magnetic field.
Okay. So which magnetic field of this infinite line, right?
Yes.
Okay. After that?
Axis.
Yes. After that?
Okay. Find magnetic field. Then we can find the current from it. If we know the magnetic field on this loop, we can find the current by Ampere's law.
But we need to find it in this loop, Mr. Ibrahim, and the magnetic field is induced here. And we need to find the current passing in this loop. So maybe who else? Maybe Taha, can you help him?
Yeah.
So can you help him?
After we find the flux, we can find the current through the flux.
How?
By getting the EMF.
By getting the
EMF.
Yeah, by getting the EMF. Yes, by getting the EMF. So guys, this, see, in electromagnetics or in the electromagnetic course, whenever a problem is given to you guys, I suggest that you just spend 1 minute or two just understand the problem and then look at your approach. Now, when the current is asked here, you know, yes, I know this is very typical. Everyone will try and say, look at the Ampere's law, which Ibrahim just now did it. And it is totally, you know, fine, because this is what, you know, comes in students' mind, that this is the Ampere's law, is the current enclosed. But here, putting it in Ampere in loop and finding this, it's not so straightforward. It's not so easy. Then you have to go for the next approach. So therefore, when you practice problems, you will see here, the best approach here is, this is your current. So the current from this, you can find the B, and that B will be external here. It will be external to this loop. This will be your B. And then from this B, can you find psi, which is the flux, which is through this loop? This is my loop. Find the flux through this loop. And once you find flux, then can you find the EMF? Yes, EMF is nothing but minus N d psi over dt. Find the EMF. And once you know the EMF, can you find the current? Yes, current is nothing but EMF over R. That is the resistance. And we know the resistance of this rectangular tube, 300 ohms. Got it? And this resistance is for the whole wire. It's not necessary. Maybe in some other problem, it may be given like this: a wire, and you will be given, instead of the resistance of a wire, 2 resistors will be given, 2 ohms and 2 ohms. Now, how can you find the current passing through this circular loop, this rectangular loop here? So in this case, again, the idea is the same. From B, first find, from here, find the B, because this B, which will be due to this infinite line, will be external to this loop. And from that B, find flux. And from that flux, find EMF. And then what will be the EMF? EMF will be nothing but, the current. The current will be nothing but, I of t will be nothing but EMF divided by, yes, R1 plus R2, this resistors. R1 plus R2. Got it? So this is the main idea behind this problem. So you can look at this problem at home. So how the EMF can help you to also find the current which is passing in the loop, which is within the vicinity of another loop. That is the main objective of this problem. Okay, so you can do it. Find I, the induced current, and you will get. Okay, so now we will go to what is called as the displacement current. So now again, I'm writing all the Maxwell's equation here. So the Maxwell's equations till now, what we have seen in our electromagnetic is this and this are the static, which is the conservation of electric field and the Gauss's law of electric field. And then we looked at the magnetostatics. This is the Ampere's law. And then this is the Gauss's law of magnetic field. So these are the 4 equations. Okay, and they are coming from different people, right? They're coming from different people. This is coming from Gauss. Sorry, this is coming from Ampere's. These 2 are coming from Gauss. and this is the conservation of electric field, then why we always use Maxwell's equation? Why we always use this Maxwell's equations? What is the important contribution of Maxwell in this? Because till now we don't see the name Maxwell here, right? When we looked at this, 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 we never heard about this guy's name. Now we are going to see what is the important contribution of Maxwell. And here what we are seeing is, now that we have already generalized this expression. See, we have already generalized this expression because this is only for static. But just now from Faraday's law, we saw that this is for only time independent, but for time dependent electric field, then you will have this expression, and the time dependent magnetic field and time dependent electric field, you will have this expression. So therefore I have generalized the first equation. So the generalization of the first equation to the time varying case, because this is time independent, to the time varying case that we studied in the last two classes, I am not changing it. So therefore del cross E bar is now minus dou B bar over dou T, or this is the integral form. So this equation is now modified to incorporate time varying fields. Now, what other equations are required to include the time varying fields? Now, for the remaining three equations, we only need to look at equation number 2, because equation number 3 and equation number 4, they are intact. That means they doesn't contradict anything when we look at the time varying fields or when we look at the time independent fields. So these two equations are okay, they are intact. So therefore we don't touch this. This equation, we have just now generalized it to incorporate both time varying as well as time independent field. Now the second equation, we need to fix it. Okay, this is the second equation. So now let's take the second equation. Now what is our argument? Our argument is, if this is my second equation, which I am looking it in differential form. See, I'm looking this in differential form. Del cross H is J bar. So if I look at it in differential form, del cross H is equal to J bar, and then I'm now just dot producting it with the del operator. So del dot, and here also del dot. Then this is the identity. We know the del dot del cross of a vector is 0. And what is del dot J bar? Del dot J bar is minus dou rho V over dou T. This is coming from where? We looked at this equation long ago when we were doing electrostatics. This equation, what is this equation? Yes, does anybody remember? Anyone? What is this equation?
Continuity.
Exactly, this is continuity equation. Continuity equation or current continuity equation. This is the current continuity equation. So the current continuity equation is saying that del dot J bar is minus dou rho V over dou T, and therefore the right hand side is equal to 0. That means del dot J bar is equal to 0, or minus dou rho V over dou T is equal to 0. But in time varying case, where your rho V, that is even your charge, becomes, if it depends on time, then this is no longer correct, because this is the case of your only static charges. Where it is independent of time. But now when you have a charges which is depending on time, because now we are generalizing it to time varying fields, then this is no longer valid. That means this is in contradiction, because in time varying case, our dou rho V over dou T will not be equal to 0. And that's why we need to correct this Ampere's law. or generalize this Ampere's law. Now, how are we generalizing this Ampere's law? We are doing an attempt to generalize that. So what is that attempt? The attempt is we are now introducing the following. So because of this contradiction, as you can see, this del cross H is J bar will not be valid for the time varying case because it is contradicting the current continuity equation. And therefore here what we are doing is we are making an attempt. And if for that attempt, what we are doing, we are adding another current density to the Ampere's law. So del cross H is equal to J plus JD bar. Okay. So we are adding this current density, another current density. Okay. Maybe we'll talk about this current density later. We are adding. Now, when we add this, now we are making sure that the contradiction is gone or not. So now again, I'm doing the dot product with the del operator on the left hand side or on the right hand side. Then left hand side becomes 0 and right hand side becomes minus dou rho v over dou t plus del dot JD bar. And therefore, my del dot JD bar is dou rho v over dou t. So in this case, if my rho v is time varying, then dou rho v over dou t is not becoming 0. And in fact, dou rho v over dou t is becoming the dot product. It is becoming del dot our introduced current density vector JD bar. So it is becoming the del dot JD bar, that is del this JD bar. Okay. Now, after what we are doing, now we are now using equation 3 of our Maxwell's equation, which is the Gauss's law. This is the Gauss's law of electrostatics in differential form. So del dot D bar is equal to rho v. So now we are substituting del dot D bar is equal to rho v in this equation. So if we substitute, this is del dot D bar here. So del is going outside, the dou over dou t is coming inside, and then interchange, when we interchange the space and the time variables, what I'm seeing that del dot JD bar is equal to del dot dou D bar over dou t. And therefore, JD bar is nothing but the introduced current density vector that we just now put it in the Ampere's law. We are seeing that in order to satisfy the time varying case as well as time independent case, my introduced vector JD bar must be equal to dou D bar over dou t. And what is this dou? This D bar is nothing but my electric flux density vector. So that's why this JD bar has a special name. It is called as displacement current density vector. Displacement current density vector. Dou D bar over dou t is called as the displacement current density vector. Or in other words, because of the time varying electric field, you will have the time varying electric flux density also. And this time varying electric flux density is nothing but our displacement current density. And therefore, the generalized Ampere's law is now this one, which is del cross H is equal to J plus J bar. And J plus J bar is now, it is J plus dou D bar over dou t. This is called as the generalized form of Ampere's law. And now this doesn't contradict anything. This is valid for both time varying as well as time independent. In time independent, this becomes 0, right? Because if it is time independent, it's a static case. So my electric flux density becomes static. So therefore this becomes 0 and del cross H will be J bar. And in the time varying case, what will happen? Your del cross H will be equal to J plus dou D bar over dou T. This is the time varying case. And this is called as the generalized form of, this is called as the generalized Ampere's law. And this is the contribution of Maxwell. So Maxwell, he modified the Ampere's law to a generalized Ampere's law by inserting this term, dou D bar over dou T. And this dou D bar over dou T has the same units because it's a current density. So it is amperes per meter square. Here, J is the conduction current density. This is due to the motion of charges. And J is sigma E bar. And dou D bar over dou T is called the displacement current density. And this is not due to charges in motion. This is purely because of the time derivative of the electric flux density. Okay, of the electric flux density. And you can also again find the displacement current density. From the displacement current density, you can find the displacement current, which is over the surface JD bar dot ds, very similar way, which is nothing but integral over surface dou D bar over dou T times ds. Okay, and therefore the displacement current is the result of time varying electric field, because this is electric flux density, electric field. And a typical example of such a current is the current passing through the capacitor when a voltage is applied to it. And this is how it, the current passing in a circuit when a capacitor is inside the circuit is explained. Okay, is explained. So the thing is, inside the capacitor or between the two plates of the capacitor, you have the displacement current density because you have an electric field created there. Because of that, you will have electric flux density. And if this electric field and electric flux density are time varying, then you will see the displacement current. Okay, so now we have the generalized form of Maxwell's equation. And that's why all these equations are called as the Maxwell's equation because of this generalized form. And now the Maxwell's equation are del cross E bar is minus dou B bar over dou T, which is our Faraday's law, or in integral form, it is this one. Second is Ampere's law, but I would say generalized Ampere's law because of the addition of this. So del cross H is J plus dou D bar over dou T, which is this one. Then the Gauss's law of electric field and the Gauss's law of magnetic field remains the same. So these are called as the 4 Maxwell's equation. And this 4 Maxwell's equation, any time varying field or time independent field, if it satisfies these 4 equations, then they are nothing but they are our electric fields, or they are electric fields and magnetic. Okay. Now the very, notice here, very important, very important, conclusion. If you see the first 2 equations, what did you observe? Yes, what did you observe? Compare this equation with the static case. In the static case, you have del cross E bar is equal to 0. And here you have del cross H bar is equal to J bar. And here you have del dot D bar is equal to rho V. And here you have del dot B bar is equal to 0. This is for the static case. Okay. And this is for the generalized one, that is even for time. Okay, now can anybody tell me the very important difference between these two? Anyone? Maybe Abdul Al Shuair, can you tell me what is the important difference between these two?
Which two you mean? The right one and
I
the
mean to
left one?
say the Maxwell's equation for the static case and the Maxwell's equation for the time varying case. Just look at this. You know, I want you to comment on the electric field and magnetic field behavior here. So are they independent? Look from the independence or dependency point of view. Anyone else can also look at it. So what do you say here? So say here, yes, go ahead.
Conservative.
Yeah, conservative is there, but I want to look at how electric field. So that's why I'm giving you the guidance. How the electric field and magnetic field are here. They are dependency on each other.
Yeah, they are independent here. And
they are independent
the left one, they are dependent.
Exactly, they are independent here. They are independent, or I would say they are decoupled. That means they can stay independently. So electric field can stay independently, doesn't rely on magnetic field, and magnetic field can stay independently. It doesn't rely on electric field. This is only the case in static. But when you have a time varying case, then you see this, the electric field is becoming a source of magnetic, the magnetic field is becoming a source of electric field. And here, the electric field is becoming a source of magnetic field. That means they are now supporting each other to exist. So they are now, they are here, your E and H are now depending on each other. They are dependent, or in our terminology, engineering terminology, we say that they are now coupled. They are coupled. They cannot exist independently. They have to rely on each other to exist. They are coupled. And this is the main reason of our electromagnetic waves and its propagation. That they are depending on each other. They have become coupled. So one is becoming the source of other. See, as I told you, the right hand side is the source and left hand side is the effect. So this is your source and this is your effect. So the magnetic field is becoming a source for electric field. Electric field is becoming a source of magnetic field. And that's why you have this electromagnetic wave, and this enabled all our wireless transmission of electromagnetic wave. And that's why Maxwell's contribution, even though it's a very small contribution of this one, dou d bar over dou t, but it was the key contribution that has enabled or that has shown the coupling between the electric field and the magnetic field in the time varying case. And that's why they are all named as Maxwell's equation. And these are the generalized Maxwell's equation. Now, just to get an idea about dou d bar over dou t, how, dou d bar over dou t will create the displacement current density. There is a small example here. Okay, we will not go into the detail, but I'll just give you some brief idea. Now we need to find the current passing through the wire, connecting the capacitor to the source and the space between the capacitors, both. So see here, I have an AC current, which I am connecting it to the capacitor. Now, if you see, the current will flow into the capacitor. You can go and put an ammeter here. You will see that there will be a current. You can put an ammeter here, there will be a current, but you will be surprised. Here you have a plate and you have a plate, and between the plates you have a dielectric. Then how come the we are forming a closed loop and the current is flowing. This is the, answer which Maxwell's gave. That Maxwell's is saying that in this region where you have the electric field, which is a time varying, it produces a time varying electric flux density, and that is responsible for the displacement current in this region. And this is what we are checking here. We are now confirming that is this really the case? So that's why we are finding the current here and we are finding the current. Okay. So first, what it is saying, to find the current connecting the capacitor to the source. So we are finding the current here. So how can I find the current here? So I know, so this is my 50 sine 10 to the power of 3t, which is my source, my voltage source. So therefore, how can I find the current? I'm first finding the capacitance. So C is epsilon S over D. I know all the dimensions. So therefore, I got the capacitance. And from the capacitance, I got the charge, because charge is CV and V is this one, right? Which is the voltage across the two terminals of your capacitor. That is your AC source. So this is the charge that I got. And once you know the charge which is staying on this capacitor plate, either this or this capacitor plate, then can I find the current? Yes, because the current is dq over dt. So find the derivative of this. Then this is my current. And this is the current which is flowing in this wire. So how I did it? I found the charge on this capacitor plate, and then I took the derivative of that charge to find the current which is flowing in this wire. Now, how do you find the current which is between these two capacitors? For that, first we need to find electric field, then electric flux density, and then if we take the derivative of electric flux density, we will get the current. So let's find the electric field here. So I know my electric field E is just V over D, right? So is V over D, and electric flux density is epsilon. So epsilon E or epsilon V over D. So here currently I'm assuming it as it is assuming it as a material with a dielectric of with a permittivity or a dielectric constant of 2. So here it is 2 epsilon times V, which is 50 sine 10 to the power of 3t over D. And if you simplify it, this is your electric flux density magnitude. And find the derivative of this. This is the answer. And now you need to find the current, because this is the current density. This is the displacement current density. To find the current, we need to integrate over the surface here. And what is the surface? The surface is nothing but my, the surface is nothing but my plate surface. Okay, it's the plate surface. See, the plates are like this. And the electric field is existing in, or electric flux density is existing in this case, right? And now to find the current, which is coming like this and going like this, that means this becomes my cross-sectional area. That is the cross-sectional area of the plate, which is given here. And how much it is? 5 centimeters square. So use the 5 centimeters square, and then you will see that the current is this one. And now if you compare this current and this current, see, they are the same. And that's why you see the current here. Of course, you cannot measure the displacement current here, because your ammeter cannot measure the current here. But it can measure the current here and here. That means it can measure only the conduction current. But whatever we have studied, from there, if we do the calculation, we find that the displacement current is this. And this is the answer to why we have a closed circuit when we have a capacitor connected to an AC voltage source. Okay, so this is the main contribution of Maxwell. Okay, so okay, let's take two simple poll questions. So is everyone ready? Okay, so here comes very simple poll questions, guys. Okay, so 40 seconds. Here it is. It is saying that a time-independent magnetic field can induce an electric field. Is it true or is it false? "20 seconds more. Read it properly. 10 seconds. 5, 4, 3, 2, 1, and that's it. Okay. I'm surprised. I'm really surprised. How many 19 students said true? Is it true, guys? Please.
No, false.
It's just false. I'm saying time independent. Time independent magnetic field can induce an electric field. It's false. This is what we reviewed just now. Time dependent magnetic field will induce an electric field. Okay. Now, next question. Okay. The expression of EMF using the magnetic flux, that is EMF is the negative time derivative of flux, that is EMF is minus d psi over dt, can only be used to calculate the motional EMF and not transformer EMF. True or false? I'm giving more time for this question. So you have 10 more seconds. 5, 4, 3, 2, 1, and that's it. Okay, here, what is the question? The expression of EMF using the magnetic flux, that is EMF is minus d psi over dt, can only be used to calculate the motional EMF and not transformer EMF. What is the correct answer? Yes, Abdullah Radwan, can you tell me? Abdullah Radwan, you are there or no?
Yes, doctor.
So what is the correct answer?
It's true.
EMF is minus d psi over dt. You can use only for motional EMF.
Yes, for the time varying.
So only for motional, not for transformer?
Oh, I thought they say on time varying.
No.
That is statistic.
See, that's why I'm reading the question in front of you guys. You know, see, can only be used to calculate motional EMF and not transformer EMF. So the answer is false. Because just now we have seen that the EMF is minus d psi over dt can be used to calculate any type of EMF. You do not need to worry about that. It will, or it automatically incorporates both transformer and motional. And Therefore, you do not need to go and identify what type of EMF is this. It will incorporate both. So if your problem generates both EMF, it will incorporate both. If your problem generates only transformer, it will give transformer. If your problem generates only motional, it will give motional. I don't know, guys. Now, I'm really okay. Please, do your best. At least I know this course is difficult, and you need to say look at this. You have to give more efforts to this course. You have to try to solve many problems. But do your best to also take as much as you can from the lecture as well. Okay, so we are doing our best. Even I'm doing my best. Especially online teaching of this course is very difficult. But still, I'm doing my best, and that's why we are almost 4 lectures lagging. And I'm now trying to give you more problems through the tutorial. I'm posting the videos, and I'm posting the tutorial questions that I did. And even after the class, I will post the tutorial that I did yesterday. So please, try to, benefit yourself, take all these, say, and practice. Okay. So now let's go to our next chapter. So if you see our now, so this actually concludes our chapter number 9. And then now we are going to the main part of our electromagnetics, where we are now considering the electromagnetic wave propagation. We will see how inclusion of the Maxwell's dou d bar over dou t, which coupled the 2 equations, how those 2 equations, when we mathematically solve it, we will see that in fact the electric field and magnetic field can propagate. And this is how, they were able to mathematically prove it, that the electromagnetic waves can propagate with the help of this inclusion of dou d bar over dou t. Okay. So again, this is my starting part. These 4 equations generalized, and we know it very well that in a source-free region. So now remember, in the magnet, so whatever we are doing here, we are considering a source-free region. That means you can think that we are considering in an air or in an atmosphere where you do not have any sources. That means your charges and your currents, they are all 0. Okay, they are all 0. And then we are now trying to look at the Maxwell's equations and solving it. Okay, so we are doing this just to simplify things, because if we try to solve these Maxwell's equations near the source, then it becomes too complicated, and which is not the level of an undergraduate. So that's why we are looking at the source-free region. And of course, these magnetic fields are generated by some source, but they are now away from that source. And if they are away from that source, now they are not in any source-free region. And in this source-free region, how they are behaving, this is what we are trying to see. So we are making J is equal to 0 and rho V is equal to 0. So we are in this region where we don't have any sources. So in this case, my Maxwell's equation becomes rho V becomes 0. So therefore, this is 0 and J becomes 0. So this is 0. So I'm writing del cross E bar is minus, instead of dou B bar over dou T, I'm writing minus mu dou H bar over dou T. So I'm writing B as mu H, and that mu I'm taking it out. And then here J is 0. Dou D bar over dou T. D I'm writing it as epsilon E, and therefore I get del cross H is epsilon dou E over dou T. So I'm writing my Maxwell's equation or in terms of electric field intensity and magnetic field intensity, E and H. Therefore, this also del dot D bar is 0. So therefore, I can write it as del dot E bar is 0. And here also del dot B bar is 0. Therefore, del dot H bar is 0. Now, if you look at these two equations, which I have already emphasized just now, we are seeing that this one. That is, the magnetic field is a function of electric field, and electric field is a function of magnetic field. That is, the time varying magnetic field is generating electric field. And here, a time varying electric field is generating a magnetic field. And these two are coupled, and that is your electromagnetic wave. And now what we are doing is we are not trying to solve these electric and magnetic field, how they looks like in a source-free region. And now we are using the Maxwell's equation. So our first objective is we will first find the electric field. Okay, let us first find the electric field. So therefore, what I'm doing is I'm taking the first Maxwell's equation, del cross E bar is minus dou B bar over dou T. And then I'm curling it with your del operator, del cross cross product. And therefore here, what I'm doing is B is mu H. So mu is coming out, dou over dou T, del cross is going inside. So it is del cross H. So it is minus mu dou over dou T times del cross H. And then what is your del cross H? And your del cross H, I'm substituting it from the second Maxwell's equation. So del cross H is over dou T or epsilon dou E over dou T. So that epsilon comes outside, and therefore you will get it as minus mu epsilon dou square E over dou T square. This is the right hand side. And what is the left hand side? Is del cross E. And this is according to our vectors. It is this one. So del dot E minus del square E. And therefore, what I will get del square E is equal to mu epsilon dou E square over dou T. Okay, so this term goes to 0. This will be your three-dimensional vector wave equation. So here we got a wave equation, and this is called as a three-dimensional because it is del. So three-dimensional spaces, spaces x, y, z, if you are taking in Cartesian coordinates, and it is in vector. So that's why it is called as three-dimensional vector wave equation. So this is how we got for the electric field. Similarly, you can get it for the magnetic field also. For the magnetic field, you can take this equation and substitute this equation here. And then you can use the Gauss's law to put here, put the equation, put it in that equation, and you will get a similar equation for the magnetic field. But we will just go for electric field, and we will see how from electric field you can get the associated magnetic field because they are already coupled. So therefore, our starting point is electric field. And now what I am doing, I am opening the vectors. So my E bar, if I take it as in Cartesian coordinates, EX, AX plus EY, AY plus EZ, AZ, then this is my left hand side and this is my right hand side. And when I equate them, equate all the unit vectors, then I will get del square EX is mu epsilon dou square EX over dou T square. Del square EY is mu epsilon dou square EY over dou square. And del square EZ is mu epsilon dou square EZ over dou T square. So now the 3D vector wave equation, we have now removed the vectors, but now we have only the scalar equations, but they are all again three-dimensional because EX can be a function of XYZ, EY can also be a function of XYZ, and EZ can also be a function of XYZ. And as I told you, in a similar way, we can get H also by using this expression and then substituting, we will get the 3 scalar equations for H. How we got it for E, we can get it for H. So therefore, there are total 6 3D scalar wave equations. And this 6 3D scalar wave equation has all the components, rectangular, because we are using rectangular coordinates, all the components of our electric field, Ex, Ey, Ez, and Hx, Hy, Hz. And therefore, I'm putting it in a more general form, which is this. So I think, guys, we will stop here, and we will take the class on Sunday, and we will have the quiz on Sunday. Okay, so thank you very much.